All right, so quiz 2 from 2021, 252. So this one asks us to draw all the atoms besides hydrogen, number all of the atoms besides hydrogen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Doesn't matter how you do it, as long as you numbered all of them. That's what the point. Then I want you to draw 3 resonance structures for the molecule below, including arrows. So I was looking for 3. Plus 2 for arrows for each one, and then plus 2 for structure or charge for each. So if you take from the sulfur, the lone pair can go there to form a new pi bond between 9 and 8. Electrons, lone pair goes to 7. Do it again, pi bond between 6 and 7. Lone pairs in that pi bond go to carbon 4. And then the lone pairs, another one, go between carbon 3 and 4 to form a pi bond. Pi bond breaks go between 2 and 1 to go to carbon 2. Have a negative charge there. It goes to 3. Different resonance structures with arrows. A lot of folks try to do too much at once and just kind of stepwise when I was looking for those 3 different ones. There's other possibilities as well. You could have just moved the electrons to one of these pi bonds if you wanted to, but that was up to you. All right, for number 2, the key here for 1 point was to add charges and lone pairs to everything. So lone pairs on the nitrogen were already there, but the negative charge wasn't. Lone pairs on the chlorine, and then of course on the products as well, negative charge on the chlorine, lone pair on the nitrogen, to make sure we added those and keeping track of those things. In B, I wanted you to identify the atoms that are the nucleophile and electrophile in the starting materials. Really, I was only looking for a nucleophile for that nitrogen, and then C1 as the electrophile. Some people did a little bit more and made the pi bond the nucleophile or made 3 an electrophile. That's okay, but really what I was looking for was this as a nucleophile, the nitrogen, and then carbon 1 as the electrophile, where the first bond is formed. And then I wanted you to draw the mechanism all in one step. So essentially what that meant was you needed to just do quite a few steps at once. So the nitrogen would react with carbon 1. That pi bond would break between 1 and 2, go to 2 and 3. The 3 and 4 pi bond would go between 5 and 4. That pi bond between 5 and 6 would go between 6 and 7, and that would break the carbon-chlorine bond to C7. Very similar to a problem we did in the workshop, the last F in the workshop as well. A little more complicated than that one in this one, though. But plus 5 for each arrow. And then finally, the bonus, why is this reaction above unlikely to happen? It's unlikely to happen because you start out with an aromatic ring and then you end up without an aromatic ring. And because aromaticity is so stabilizing, that's unlikely that would happen. Last question, number 3. Indicate what hybrid orbital each lone pair is located in the box molecules below. So first, you could actually label each of these as aromatic, anti-aromatic, or non-aromatic. And remember, most things are non-aromatic, and very few things are anti-aromatic because it's so destabilizing. And things will be aromatic if they can. So this compound is aromatic. How do I know that? Ring, it's in a ring, and it's an uninterrupted conjugated pi system. It has 1, 2, 3 pairs of lone pairs of electrons. That's an odd number, so that follows Huckel's rule. And this is aromatic. And the way this is drawn here, this lone pair has to be in a p orbital. So it'd be part of the p orbital system and be aromatic. Same with this one, this cyclopentadiene anion. 1, 2, 3 lone pairs in the ring, uninterrupted pi system. This carbanion is choosing to be sp2 hybridized. So then it has that lone pair in a p orbital. So it's uninterrupted p orbital system. And that would be aromatic, and that's where the lone pairs are at. Dicyclobutadiene. This is anti-aromatic. It's in a ring, uninterrupted p orbital system. 1, 2, 2 pairs of electrons, and that's an even number, so that'd be anti-aromatic, very destabilizing. 3-membered ring with 1 pi bond and an empty carbocation, uninterrupted p orbital system. Carbocations are sp2 hybridized. There's an empty p orbital. There'd be one pair of electrons in the system. That's an odd number. That's aromatic. Finally, this system, it's in a ring, but it has an interrupted system. That's an sp3 hybridized atom. Therefore, it's not all sharing, so this is just non-aromatic. Normal type molecules are mostly non-aromatic. Plus 1 for each of the lone, which hybrid orbital the lone pairs were in, and then whether things were aromatic, anti-aromatic, or non-aromatic.